So we have a rod in a horizontal plane. There is a particle whose mass is very less than the mass of the rod. It comes to the, let's say this is x-axis, this is y-axis. It comes to the x-axis, the velocity vector is towards x-axis. It hits the rod at point A. It's a completely inelastic collision. That means the point mass m, small m, would stick to the end A of the rod. Now this is a normal situation. You might have done multiple questions similar to this. But one thing you might have noticed, we always assume, or we always, you can say, take for granted, that if the rod is not fixed, it can rotate about any axis, then we know, because that's how we have been told, that free body would rotate about its center of mass. Now give it a pause, this video, and think, why would this rotate about center of mass after the collision? And why would it even rotate? Center of mass is secondary. So give it a pause and think about it. Okay, let's discuss. So let's say, so how many parameters do we have? We know this is in a horizontal plane. This whole event is taking place in a horizontal plane. The point mass moves straight towards x-axis, perpendicular to the length of the rod AB, collides and sticks. Now there is no external force on this entire system. There is no external torque in this entire system, on this entire system. So that means, what does it tell us? The net linear momentum and the net angular momentum will be conserved. So this objective is to check if the body, this combined body, would rotate about the center of mass of the rod. Center of mass would not change much because we have assumed small m is very less than capital M. So center of mass would be at the same point here. Let's say this point is C. So now we'll calculate the velocity of this combined system, because the mass is attached here. Let's say after time t, this rod comes here. We have assumed that it's not rotating, so the rod is moving like this. After the collision, it's moving like this, with the mass m attached here. Okay, no rotation. So in this case, obviously the mass small m will have the same velocity as that of the entire rod, and this is moving with a velocity of VCM. So obviously the small mass would also be moving with a velocity of VCM. Now, applying linear momentum conservation, we have initial momentum mv equals final momentum. Final is small m plus capital M into VCM. And it's been given, and it's very less than M. So from here, if you calculate VCM, it will be so as you can see, this value is large, this denominator is very large. That means VCM will move very slow. Okay, that is very intuitive, that makes sense. So VCM is very less than V. Okay. Now what about the angular momentum? We know this equation. The rate at which the angular momentum changes is equal to the net torque. Here there is no torque. So that means L must be constant. So let's choose a point anywhere and the angular momentum must be conserved about that point. That point could be anywhere. So we can choose any point here, 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 here. But the calculation would be very complex. So let's choose a point very smartly and conserve the angular momentum about that point. So let's say we have a point P here. Let's conserve the angular momentum about P before the impact and after the impact. So before the impact, what was the angular momentum? mv into this perpendicular distance. This is the v vector, this is the distance. How much is that? L by 2. So initial angular momentum is mv into L by 2. So here Li okay, L final, because we have assumed it's not rotating. So the center of mass will have a momentum mv, linear momentum, but this velocity vector will go through point P. So mv into r, angular momentum, will be 0 because r is 0. So the angular momentum of the center of mass will be 0 plus the angular momentum of this small mass, that will be mvcm into this distance, that is L by 2. Okay, now let's see. L initial upon L final. Let's see how many times it has increased or reduced. From here. Cancel. So here you see VCM is very less than V. So that means L initial is very high than L final. That means some angular momentum was lost in this whole process. Now again take a pause and think where that extra momentum disappeared and what will happen. What will actually happen so that the angular momentum is conserved. So now you might say, okay, the rod will start rotating about any other point here or here. Let's say this point, but that would be incorrect. Why? Because if the rod rotates about this point, this center of mass will have to rotate about this point also. But it cannot do that because linear momentum is conserved. The initial linear momentum was in the x-axis direction. So the final momentum will still follow the x-axis. It cannot change direction. So the VCM must move towards x-axis in a straight line. So that means if the rod has to rotate, it will only rotate about the center of mass, not about any other mass. And it has to rotate. Why? Because there is no other way momentum can be conserved. The angular momentum can be conserved. You can see here, initial is very high, final is very low. So that extra momentum is provided by the rod's rotation about center of mass. That is called I omega. So hope that is clear now, why the rod will rotate and why it will rotate about the center of mass, not about any other arbitrary point on the rod. Thank you.